All right, solubility. Okay, so we went over quite in depth of metal, non-metal stuff, how ionic bond and covalent bonds a couple of weeks ago, right? So this solubility has a lot to do with actually the bondings and in how we were drawing the I have another student coming in. When we were drawing the Lewis structure, and one of the importance of Lewis structure is it tells a lot about how molecules are shaped, and the shape of molecule or the characteristic of the molecule will tell us a lot of information about it, whether we want to know or not. But if you kind of dig into it, it kind of tells us a lot of stuff. Okay, so let's kind of briefly go into that little bonding part. Remember we had an ionic bond, right? So we had ionic, okay, that combined with what? Metal with non-metal, right? Okay, so when you're looking at the periodic table, right? We were around somewhere here, like a ladder looking part. This is with the metal side, right? And this was a non-metal side. Okay. And what happens the most of the time is what? Metal side is positive charged, non-metal side is negative charged, right? And then they come together as attraction force. They form a little, I guess, salt, right? So-called salt, meaning that what? Metal and non-metals are combined together. So this is where the actual polarity. There's a key word here is a polarity. Okay. So when we look at magnets, right? We have a one side is N, one side is S. This is a polarity, right? So what it means to a compound, a chemical compound, is that one side is positive, which is metal, one side negative. Well, this is as polar as they can be, right? Of course, you can have a positive 3 charge to negative 3 charge. That could be the most polar, but it doesn't matter. As long as we have a metal and non-metal coming together, that's a polar. Okay, let's kind of reverse back to our water. Okay, because all the solubility has with the water, and some that we will probably deal with nonmetals too, but I don't think in general chemistry we deal with the nonmetal to nonmetal solubility as much. But we'll get into that briefly later on. So let's look at water. Okay, so when we are drawing the Lewis structure of water, it's H2O, right? And we didn't draw that fashion, right? Why was that? Why was the reason? What was the reason for it? Okay, remember how we are drawing that into three-dimensional, where we are drawing water in a little bench shape, right, with the two lone pairs hanging around. Okay, so if we're going to that three-dimensional shape that originated from CH4, right, this is a methane, where central atom is a carbon, and we have one hydrogen on the plane, one hydrogen on a plane, okay, and this comes out of the dimension of the plane with hydrogen. They go into the dimension of the plane with hydrogen. So this has a tetrahedral shape, right? We had a triangle like this. There you go, right? Tetrahedral shape. So what happens here when it comes to water is we are literally taking two hydrogen out of it, okay? And instead of that, we are replacing that hydrogen with the two lone pairs. That's what it is, basically. And the central atom, of course, is not going to be a carbon, it's going to be oxygen. So basically what happens is we have oxygen in the middle, and these two spaces are taken up by what? Lone pair electrons. And then we have this two hydrogens hanging up with oxygen. Okay, so I should have drawn the other way. Hydrogen, hydrogen. So if I were to draw it in two dimensions, it would look like this, basically. Okay. So what happens with this water is that we have to think about something called electronegativity. I'm not sure if your teacher talked about this. In short, what electronegativity means is that you have a francium here and you have a fluorine at the edge of it. Of course, except that none, what is it? This is a noble gas part like a helium, neon. We don't care about that part in terms of electronegativity wise. So starting from francium to fluorine, what happens is the electronegativity increases from here to here. Okay. What is electronegativity? Electronegativity means that in each term, whoever wants the most electrons or withdraws electrons from the neighbors. It's like a willingness to withdraw electrons from the neighbors. So that means the francium is the weakest and fluorine is the strongest. Okay, so it wants to bring electrons from the neighbors. Okay, so that means it's coming from francium, the least willing to pull electrons from the neighbor, all the way to fluorine is the most electron pulling electron from the neighbor. So if I will go a little bit deeper on this section of it, it goes B, C, N, O, F. So this is the most among these five, and this is going to be least among the five. So if you look at hydrogen, which is this right here, but actually the electronegativity, the strength of the electronegativity of hydrogen, it sits right between boron and carbon. Okay, that's where it sits. So if you look at the, in terms of water-wise, you have an oxygen here, and you have a hydrogen here, and then who is more willing to pull electron from the neighbor? Compared to oxygen to the hydrogen, oxygen is more willing to because it's closer to the fluorine side, right? Remember, trend goes from the lower left corner to the upper right corner, right? Electronegativity, who's more willing to pull electron from the neighbor. So this oxygen has a higher electron pulling force compared to the hydrogen. Okay, so what happens is electron gets pulled away, even though it has two lone pairs of electrons here with oxygen. Its oxygen is pulling more electron than even hydrogen has. So remember that electrons are when electrons are traveling between two to make a bond, they supposed to have a somewhat of a sharing of electron going back and forth with the oxygen and hydrogen. But because oxygen is pulling more electron toward oxygen is pulling more toward the oxygen away from hydrogen, the orbital, if I were to exaggerate it, orbital of that bond will look like this. Okay, so this side, so electrons are staying more on the oxygen side than the hydrogen side is. Okay, same way in this part too. Okay, so now what happens is that this unequally shared electron causes a partially, and partial charge is shown as a delta. Okay, this is a Greek letter of a delta. Okay, partial. This side is going to be, so this side is going to be partially negative because what? There's a bunch of electrons are here. Compared to this hydrogen side, the electron was pulled away, so it has a partially negative charge, a positive charge, right? Partially positive on both sides, and partially negative here. So if you look at this as a magnet perspective view, you clearly have a one side is a negative, one side is positive. This creates a polarity. Once again, important word, polarity. Okay. So when we look at salt, meaning that quote unquote salt, not actually NaCl as a salt, right? Any metal, non-metal compound tend to be called as a general term as salt, right? So just in case as a example, KCl, okay? Potassium chloride. It's a metal with a non-metal. So this is a polar compound. CPD, compound, I'm writing as a shorthand, okay? Polar compound, okay? So we have a polar compound, which is what is also what? Ionic bond, right? Remember that, ionic bond. That's going to be mixing with water, which is also polar. So the term here is like dissolves like. What does that mean? If you have a polar, then polar compound will dissolve well with the polar. That's why when you dissolve salt, the table salt that you eat at home, in a water, you mix it, what happens? It dissolves pretty well, right? Because that both are polar compound. Let's compare that with a molecule that is nonpolar. Okay. So we have a probably one of the easiest one is going to be, let's say, oil. Okay. The oil has a bunch of carbon. I'm not sure how many carbons are there, and a bunch of hydrogens in there as a structure. So this X means very many of them. Okay, I don't know how many. I can find it, but then Who cares? It's just a whole bunch of them. Okay, and when you look at once again periodic table, okay, hydrogen is here, and oxygen is here, and oh, actually carbon is here. Okay, let me rewrite that. BCNOF, BCNOF. So carbon is here. Remember, hydrogen actually is a nonmetal, but it sits as a metal side just because it has a positive characteristic. But it's actually nonmetal. It's supposed to be here. Okay, so we have a compound that is made of everything but, nothing but nonmetals. Okay, so nonmetal compound in general that you will have anything that is what? Nonmetal with a nonmetal. Okay, which is, well, maybe I should have written as a covalent compound. Covalent compound is made of nonmetal to nonmetal. Okay, hydrogen nonmetal, carbon nonmetal. So, and the thing is that, remember BCNOF, looking at the electronegativity, which hydrogen sits right between these two. Carbon and hydrogen, the electronegativity difference is very, very close to each other. So what happens if I were to look at one carbon and hydrogen? Of course, carbon is slightly higher than hydrogen is, but this hydrogen and carbon, the difference of pulling force is not that much a big difference. Okay, so if I were to exaggerate that orbit between two, yeah, sure, maybe a carbon has a little bit slightly more, but it does not make that much a difference. Yes, it will still have a partial negative on that side and a partial positive, but the difference of this is not that big. And number two, let's kind of try to draw that CH4 again. Okay, so we have this going on. Okay, and they're all equally distributed out, right? Remember, that's where we're having a carbon is pulling electron away from the hydrogen, right? But then it's all pulling that directions from all over. And this is like a tug of war where everything, so let's kind of put it this way. You put your two hands together and push each other, same strength. Does it go anywhere, right? You have a hand here, okay? You have another hand here, pushing against each other on top of it, okay? So you're forcing here, forcing here. You're pushing same force. It's not going anywhere, right? So that means when there was not really tug of war, it's a pulling force. It's not really pushing force. Let's just say they're pushing each other, right? And there is no, so net force of pushing each other is equal, then it's not going anywhere. It's not moving that direction or the other direction either. So same thing, electrons are withdrawn to that all directions, right? And of course, there is very, very small partially negative charge here. Positive, 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 very small compared to water. This creates nonpolar compound, even though there's a polarity. So there's a polarity, of course, between each legs, right? There's polarity between each leg. But the pushing into force is all equal to each other, makes it as a whole compound as a what? Nonpolar compound. So when it comes to polar, mixing with nonpolar, this is not a like dissolves like. They are not likes, right? Therefore, what? No mixtures. Well, I mean, I guess you can't form a solution, meaning that you cannot dissolve them. That's why you have when you have oil and a water. Okay, water will sit on the bottom, and oil will sit on top. And I'll put that as water. They have a distinguishable separate layer between two. Okay, why oil sits on the top? Well, I mean, in terms of a cooking oil that we drink, well, no, we don't drink cooking oil, that we use to cook compared to water, it's just because of density. Okay, whatever is less dense, it floats. That's how woods are flowing on top of water, right? Density of water is just tend to be higher than the oil is. That's why it sits higher. If you were to put like some kind of crude oil that you pull out from the ground, that has a much higher density than the water is. Therefore, that crude oil actually will sit below water. So it's all about density. Okay, that's only the difference, right? So that's what the light dissolved light is coming from. Okay, so when you are actually doing this, you have to know how to draw the compound. Think about the polarity by using this, what? Now you don't want that. Using this, where what? Electronegativity, right? Being weakest electronegativity to the strongest electronegativity, compare the pulling force, and then find out through drawing the structure and see if they are equally or unequally sharing. So once again, we go back to the water. Water had this, right? Having a shape of a bent shape, but with what? We have a polarity going on like this, and the strength of the oxygen is much greater compared to hydrogen was. It gave that unequal sharing of electrons, permanently making that partially negative, partially positive. Yet there is a polarity here, right? But each polarity is facing the same direction, neutralizing all the forces, causing it to nonpolar. Okay, so that's the difference, right? So here are only two legs are, which heading to what? The polarity heads to that direction, right? Polarity heading to that direction, from positive to negative, positive to negative. Here, from positive to negative, right? Positive, negative. But they are pointing to one direction where it is pointing one direction, but there are only two of them. So you kind of think about it this way. You have a rod here, and you are pulling, you're pushing from two directions. Which direction would this pole actually, I guess pole is going to be pushing to that direction, right? Simple physics, right? But when you have it here, you have a pole here, and you're pushing from all four directions opposite to each other. Well, this pole is not going anywhere, right? That's what this is. And this is going to be what the water is. That creates polarity, okay? And this creates what? Nonpolar. So in general, whenever you see a bunch of carbon and hydrogen in it, you could definitely consider as a nonpolar compound, okay? That has with a lot of nonpolar compounds in here. But you have to still what? Draw. If this thing happens, even though oxygen and hydrogen is covalent compound, which is between nonmetal to nonmetal, but what? Once again, electronegativity difference is pretty great. That creates this polarity, and not only that, the shape of it creates that one side polar, one side the other side also polar as a positive and negative. That creates a permanent magnet. Compared to this one, also creates polar, but pointing into one direction, canceling out all the polarities out, creating to nonpolar. Okay, that's the key. Okay, so another thing you have to consider is like alcohols. So ethanol, which is CCOH. Okay, so this is ethanol. Okay, so C2H6O, I believe. Yeah, but easier way to write is another way to write C3H2, CH3CH2OH. This is ethanol. Okay, basically our base part of the alcohol. So let's kind of look at this one. Okay, if you look at on this side, okay, we kind of studied about that earlier, that's just before, right? Bunch of carbons and hydrogens, right? This side is a nonpolar region. Yet, what do you see here? You have a oxygen and hydrogen. Okay, so remember, once again, BCNOF, hydrogen being right here as a polarity, right? Oxygen is strong electronegative, right? Negative, right? Compared to everyone around it, which is hydrogen carbon. Okay, so electrons are withdrawn to the oxygen. So I'm going to exaggerate that, creating that. So from even carbon, even though carbon is stronger than hydrogen, it's still weaker than oxygen is, right? So pulling away electrons, okay, creating partial negative, partial positive. And even this is a partial negative, a partial positive actually. This carbon will draw electron from the neighbor of the hydrogen too, right? So this is not really going to be negative, positive there actually. Okay, but just as looking at this. But why am I drawing this as a bent shape? Once again, what does oxygen have? Always when you have an oxygen, combined with whatever compound it has, whatever element it has, there is going to be what? Two lone pair electrons, right? That's why we are drawing as a bent shape. So there should be two lone pair electrons here, creating the bent shape. Okay, so this is a polar. So would ethanol, which is alcohol, would mix with the water? What do you think? Okay, put a little thought on this one. Okay, we have a nonpolar region, but yet we have a polar region here. All right, so basically what will happen here? Okay, is because it has a polar region, yes, it will be attracting to water. So you have water here, partially negative, partially positive. So this partial positive, partial negative, I should rewrite that again so that I'm confused. Partial negative there, let me rewrite that. Okay, partial negative, partial positive. So what will happen here is this partial negative will be attracted to the partial positive of that hydrogen, and this partial negative will attract to that partial positive side of the hydrogen. Okay, so they will mix into it, but it will avoid that nonpolar. So when you mix later on, if you ever, well, I guess one of you guys is actually teen, so you should not be doing this. But if ever have your uncle or your father is drinking, try this. You have some kind of alcohol, say beer or some sort, okay, and try to drip in few drops of water into that cup. Okay, you will see a little kind of if this is a cup and this is a beer, and if you drip water into it, okay, a few drops, you will see some kind of a little haziness on that part, and it will eventually dissipate. So what happens is this water molecule getting dropped onto the beer is actually, it takes time unless you stir it, which quicker. If you drip it, you will see a little haziness of that area, and then eventually disappear, meaning that the beer with the alcohol part, with the OH, is trying to mix with this water. So they are trying to find the area to get attracted to each other. Okay. So whenever you see a molecule with OH in it, it will dissolve to the certain degree. Okay. Why am I saying to the certain degree? Because if this part gets much longer, okay, this non-polar region gets much greater than the polar region, the solubility will drop because this non-polar region will dominate over polar regions. Of course, you will still have that water molecule still trying to look for that area to get attracted, but compared to that huge non-polar region to the polar region, it's not going to be easy to find the area for the molecule to seek for that polar area. Okay, so it will be much slower, I guess, mix, but it's not going to be really mixing. So think about like what is it, crude oil that you see like pumping out from the ground. It is liquid, but it's a whole. Everything is what basically what non-polar stuff. You pour water on top of it, it's not going to mix. Definitely, you will see like water level and then oil level totally separated. Even though there is a OH part, maybe part of that crude oil in there too. Okay, so that's what that part is. And I think there's a few more topics that the Professor Chai wanted to cover. Alright, let me double check here, and goes into solutions. Okay, colligative properties. Okay. And Lewis structure and determination of polar not or not when that is well dissolved in water. Okay, yeah, we just talked about that. Freezing point, depression. Okay. All right. So let's pull out my textbook. That would be good timing. Okay, hopefully things are clear at this point. And took care of that part. Okay. All right, here we go. Let's go into navigation panel. All right, colligative properties, solutions, Charles law, gas law. Okay, there you go. All right. So let's kind of go with the basic of it, what it means by colligative properties. Different colors. Okay, a solvent. Let's kind of clarify what solvent solute is. Okay, solute versus solvent. I'm gonna use it as a salt and water, meaning that what happens? Salt dissolves in water, right? So what happens here is solute dissolves in water. I mean in solvent. Okay, so solvent is water, solute is salt is going to be solute. Okay, so solvent, which is water, property can be altered by adding chemicals to it. Okay, what does that mean? Okay, even if water has a certain solubility, okay, ability to dissolve, by changing parameters around it, it could create a different level of solubility, meaning that can it dissolve more or less. Okay, so there are a few things here that we can deal with is that lowering vapor pressure. Okay, I think you might have dealt with this vapor pressure with a gas chapter last week. Okay, boiling point elevations, freezing point depressions, and change of osmotic pressure. I'm not sure about this one, but at least these three are most common. Okay. So what does it mean by lowering vapor pressure? Okay. So let's go into that topic here. Okay, oops. Okay, so let's take a look at here. So vapor pressure was not that okay with the previous concept of vapor pressure. So let's kind of briefly go into vapor pressure is. Okay, we have a closed container. Okay, this is water. Okay, and if you leave your water bottle, okay, let's say this is one of the clear water bottle. Okay, oops, that looks too fatty. Okay, clear water bottle. Okay, you had a drink before you go out of the car. Okay, water is about that level. You come back later on at the later day. The day was pretty hot, and then what do you see? You see kind of little droplets on the side in the evening hours. Okay, no one shook your car, but water is kind of somewhere in there. What happens is the water evaporates in here. And then when the surrounding gets cooled by evening, surrounding gets cooler faster than the water itself, creating that condensation of droplets to the side where the cooler area is. That creates collection of all these waters on the side of the wall. That's where you get the water droplets. And you know, it's kind of easy when you actually go out for a little coffee, like especially cold drinks that you get. Okay, let's go to Starbucks. Okay, here's a lady with the long hair with the fin on it. Okay, you have a cold drink. Okay, so here is a straw. Okay, as time goes by, what happens? Your outer side start having all these droplets. Well, is water from inside seeping out? No. What happens is all the air around it, warm air around it, carries some amount of a water molecule with it. Okay. And when it meets with the cold surface, the water that was in the vaporized water in the atmosphere, it condenses on the surface, creating all this water molecule. Okay, so what does that mean? In every given temperature, okay, every given temperature, there is a maximum amount of water that can be evaporated. Okay, every given temperature, there is a maximum amount of water that can be evaporated. Okay, so going back to that water bottle again. Okay, let's say at 25 degrees Celsius, you found out that there are 100 droplets, well, not droplets, the water molecules are evaporated. Okay, that says 100 water molecules. Okay, at 70 degrees Celsius, let's say it's a really hot day, and you found out that there are about what? Let's say 250 water molecules are evaporated. So as the temperature goes up, your water molecule is going to increase. That means what? If temperature drops below, so let's say 10 degrees Celsius, now you only have 50 water molecules are in here. Okay, everything else will be condensed. Okay, so going back to here, now that we know what the vapor pressure, so the vapor pressure, what it means is that as temperature goes up, the pressure of the vapor increases in here, right? Because you have a more water molecule with a higher temperature, right? Simply thinking. Low pressure, low vapor pressure means that what temperature is low. Okay, that's what the relationship is. So let's kind of think about it this way. You have a water bottle here. Okay, compared, this is a pure water. Now you have another water bottle. Just consider the same size. Okay, same amount of water, but this actually has a salt in it. Okay, what does salt do in water? Okay, they dissolve into what? Na plus and Cl minus. Okay, this is where the solution react. I guess more of a how this water behaves around these ions is a key here. Okay, let's kind of roll back a little bit. So what happens here is Na plus, looking at the Cl minus. What happens is, remember, water actually has a polarity, right? Partial negative, partial positive. So you may ask yourself, okay, you know what? Okay, salt dissolved as a partial negative, as a positive and negative compound, well, element, or as I like more like an ion in a water. Well, they are positive and negative. How come they don't come back together as an NaCl again? Which it should be, right? But what prevents is water. So what happens here is this positive charge of a sodium gets neutralized by water, oxygen side of water. Because what does oxygen side water has? Partial negative, right? So what happens is water is going to be going against this sodium, and all the oxygen is be facing toward that direction, which is negative side. For the chlorine, which is a negative charge, will be facing with all the hydrogens around it. Okay, so it look like this. The water will have this thing going on. So if you look at here, diagram here, this is what's happening. Let me actually get that bigger. Look at that. Okay, you can see this is the water molecule, this is chlorine, and this is a water molecule with what? Sodium. And you can see the oxygen side is the blue one, and the red one is going to be hydrogen side. And you can see how it's facing each other. So because water is neutralizing that charge of the positive and negative, they don't have a chance to come together. And they dissolve as a Na plus and Cl minus. Okay, so let's put it that way for now. Alright, so we gotta roll back a little bit back. I am not sure if you actually did study about hydrogen bond. Okay, let's kind of briefly go with that. I know we're jumping a lot of topics here, but this actually connects with this topic, so we have to know. Hydrogen bond has to do with Fawn. What does it mean? If you look at the CNOF, okay, fluorine is the strongest electronegativity, right? We talked about that. Okay, these are the fawns. F-O-N, F-O-N, fawn. Okay, think of it as a phone, right? Like when you're talking on the phone. Fawn. So what does it mean? Whenever you have oxygen neighboring hydrogen, like water, has another molecule neighboring of same kind. Oops, not the plus sign. Same kind. Meaning this hydrogen, once again, this hydrogen has an oxygen as a neighbor within the molecule and another oxygen as a neighbor with a different molecule that creates something called hydrogen bond. Okay. Okay, there you go. Okay. What if we have fluorine HF, okay, hydrofluoric acid. Okay, this hydrogen here has a neighbor of FON, one of the FONs, which is oxygen, and then the neighboring molecule has a F, which is part of the FON again, creates hydrogen bond. Another example, ammonia, okay, has a neighboring molecule of what? This hydrogen has one of the FONs as a within the molecule and another one of the FONs as a neighboring molecule, right? So they all have hydrogen bond. Okay. So what we have to compare here is the strength of this hydrogen bond and then compare to the bond between the sodium and the water. Okay, let me actually do it with different color. Okay, earlier remember we had how sodium ion gets neutralized, the positive side gets positive charge gets neutralized by oxygen side of that negative, partial negative, right? Partial negative here of oxygen. Okay, they're all doing that right now. Okay, so we have to compare the strength between this compared to that. Okay, why? Let's kind of put it this way. So when water is trying to evaporate into this empty space, okay, whatever temperature it is, what does water molecule has to break off from? Okay, when you're in water, water has nothing but water, right? Just a whole bunch of water all the way around. Okay, so we have attraction forces, right? And there's another water here, okay, all the way around, right? So what this water, in order for this water to come out of that break apart and come into this empty space, it has to break apart hydrogen bond. Okay, which is what? Basically, remember we talked about this again earlier. This has a polarity, right? Created by, what was it again? Electronegativity. Once again, BCNOF. Hydrogen sits right here. F is the most strongest electronegativity and goes weaker, right? And this shape of the molecule creates a polarity, right? Creates a partial negative, partial positive. Nitrogen also is here compared to hydrogen, stronger electronegativity, so it draws electrons toward that directions. So you have this going on here too, creating partial negative here, partial positive here. So partial negative, partial positive, partial positive, right? FH, of course, F is right here, H is right here, therefore huge difference of electronegativity, therefore it creates partial negative here, partial positive here. Same thing with the water, partial positive, partial negative, and there's a connection between two, right? So basically, once again, for this water to come out of the surface and stay in here, is to break apart the hydrogen bond. Okay. Now let's look at this one. Remember, these are, think about this way, these are partial charges. Okay, that's a key here. Okay, now take a look at this one. I'm gonna erase that part and then draw it a little bit more closer. Okay, so we have Na plus here, oxygen here, and there is a, let me draw it with a different color. There's a bond. Okay, now we want to know what kind of bond this is. Okay, of course we have a polar region of water, right? Partial, can I keep writing partial negative, partial positive here, right? But this is what? This is a full charge. This is not a partial charge. So now the attraction between sodium ion with the water is full charge with partial charge, right? Where all this thing, especially between water to water, has what? This is a partial charge. This is a partial charge. This is a partial charge. Everything is partial charge. So, kind of think simply. You have full charge with the partial charge attracting each other versus partial charge and partial charge attracting each other. Which one do you think is going to be stronger interactions? Of course this one, right? So, if you want to have this water to be disconnected and then come out of the water, you will have a harder time for this water to come out because of the bond is greater here than the regular water all the way around. Okay, hope that's clear. Okay, once again, going back. Because we have a full charge with the sodium ion and a partial charge with the water, the interaction between two is greater than the partial to partial. Because the interaction this is greater, the water has a difficult time to come out of it. Okay? So, what's the boiling point of water in 25 degrees Celsius? 100 degrees Celsius, right? So, when 100 degrees Celsius, this is our boil, a whole bunch of vapor is going to be here. Now, at 100 degrees Celsius, you will still see, with this one, you will still see a whole bunch of water vapor, but not as much as this one will be, because you have a sodium that is holding on to that water much longer. So what happens here is you have to heat it up higher, let's say 102 degrees Celsius, to have a same amount of vapor in here when this is 100 degrees Celsius compared to 102 degrees Celsius. This is a colligative property. You are changing the parameter of a solution, actually water, by adding in different things or subtracting different things to create the change of a property of water. That's a colligative property. Okay, so we just had one example of elevation of boiling point by adding things. Okay. I mean, I'm not sure if I'm going too into depth of a theory, but then it will give you understanding of why, at least. Okay. So that's basically what this is talking about eventually. Okay, so we gotta talk about something called Van Hoff factor. Okay, what is Van Hoff factor? Simply, if a compound is dissolved in water, how many of sub-compound or subsection of this compound will be dissolved in water? For instance, you have NaCl. If it dissolves in water, how many parts, subparts does it become? Na plus Cl minus. Oh, there are two of them, right? So Van Hoff factor, which we symbolize as an I, is equal to 2. Okay? And you may say, hey teacher, doesn't sugar also dissolve in water? But sugar is a covalent compound. Yes, it is. Sugar is C6H12O6. Okay, it's a hexagonal shape with a little leg on here. Okay, and the thing is, this does dissolve in water, but basically what happens is this whole compound dissolve as a one. It does not get broken down into hydrogen, oxygen, and carbon. It does not. The whole compound dissolve as one. So what the difference, remember, compared to salt was what? Salt dissolve into an ion, where sugar does not get broken into each pieces. It stays as one, but it still dissolves in water as a one whole thing. So this is, yeah, it is soluble, but it's a whole different characteristics, right? When you are creating an ion, and this does not create an ion. So the Van Hoff factor of this, even though it has a whole bunch of stuff in it, I is 1. Okay, why does it dissolve in water with nonpolar stuff? Oh, because there's a bunch of OHs in it. Remember we talked about that whenever there's an OH in it? Let me actually show you the actual compound of sugar molecule. Okay, glucose. Glucose molecule. Okie dokie. So here's a glucose molecule. Okay, you see a whole bunch of OHs, right? This is where water gets attached to and dissolve the whole thing as a one piece. Like I said, it's not broken down into pieces. The bonds here does not get broken off. It dissolves the one whole thing. Okay, that attach all the water attached to this. Remember earlier we talked about beer, right? The beer dissolves in water, while water dissolves in beer. Either way, and because it has OH in it, the OH is the key. Okay, amount of OH versus amount of nonpolar stuff. And this is enough amount of OHs for sugar to dissolve in water. Okay, like I said, once again, the bonds do not break like what the salt is doing. Okay, that's the difference. Therefore, because the whole thing dissolves as one, the Van Hoff factor, which is broken pieces, is 1. Okay, why is that important? Because it's part of the equation that you're going to be dealing with. Okay, so if you look at here, we are looking at find the vapor pressure of water 25 degrees Celsius for solution made by dissolving 100 grams of potassium sulfate. Let's take a look at that. Potassium sulfate. Is this soluble or not? Well, let's take a look. This is what? Metal. This is non-metal, right? If you look at periodic table, let me pull up periodic table. So periodic table, here we go. Okay, so we have sulfur here, oxygen here, potassium is here. Okay, we're talking about definitely metal to non-metal stuff. Okay, another way to know the solubility of this, remember the solubility charts that we showed last time? Let me pull out the solubility charts. It's in my Discord channel that you can go into and download the solubility rule. Let me actually pull that solubility rule. Lecture topic, no reference and resources. There we go. Solubility charts. I'll download it now. There you go. Okay. If you look at group 1A, let's go back to the periodic table once again. Oops, too big. Okay, this is group 1A. This is group 1A. So what does it say? Group 1A is always soluble, right? Except lithium phosphate. Okay, don't care about that right now. Okay, potassium is part of group 1A. That means no matter what it has attached with, it will always going to be soluble, right? So that means when we dissolve this in water, what's the like subcompounds, well, sub-particle or component of it? Okay, that means what? You have 2 potassiums and 1 SO4 minus. This is non-metal stuff. They don't dissolve in terms of each little piece is going to sulfur and oxygens. Okay, like how sugar did. This one whole piece is going to dissolve in water. So now, how many parts are this? There are 3 parts into this, right? So your Van Hoff factor, which is the I number, is going to be 3. Okay, so what happens here is you have that K2SO4, 500 grams of water, right? So you are trying to look for the partial pressure of it. Okay. So let's kind of go down one more time. Scroll down a little bit. So you have, oops, not that side. You have this here as a mole of potassium sulfate. So we're trying to find out how many moles of these are, number one, because we have to know how many the total amount is, because they were giving us a grams of it. So we have 100 grams of K2SO4. This is what? Molar mass from the periodic table. Okay, so we are switching over from grams to mole here. And you have a moles of water that was given in the question, and switching over to the grams of water into moles of water. Okay, so once again, Van Hoff factor is 3 because what? We have 2 of the potassium and 1 of the sulfur. So I is 3. So we have a equation here looking as the partial pressure of pressure water. Okay, no, mole fraction of water is a mole fraction of water itself, a mole of the water itself with whatever dissolved in it, the total amount of it. So we have a mole of water and then mole of potassium sulfate, because remember we have we have a container here, right? We are adding water and then K2SO4. So the total amount is amount of water plus amount of K2SO4, which is bottom here. We're creating a mole fraction of water. So total over whatever we want, which is water. Okay, this is what the bottom is. That's how we create a mole fraction. So we have that here in terms of mole, and that's a mole fraction. So we have a 0.92. That means 92.93% of the whole thing is water. That's what this means. Okay. We plug that into the equation. Let me actually blow it up a little bigger so you can see it. Let me get rid of all that stuff and let's get it bigger. Okay, there you go. Okay, so we bring that number to this x, okay, mole fraction, and then the actual amount at the standard, this is the given number, and you just multiply, and that gives us what? 22.1 millimeter mercury. Remember, it's a vapor pressure, right? So pressure is this is millimeter mercury is a pressure unit. So the actual, when you are at the standard position where there's only water, you should supposed to have a 23.8 millimeters of mercury pressure was supposed to be given. But because you dissolved water, well, not this is water, this is a potassium sulfate into water, creating all that positive, negative stuff, and water gets attached to it, the pressure became lower because water has to overcome that attraction forces with water and all these ions that was created. Okay, so it has a lower amount that gets vaporized into the space. Okay, hopefully this clarifies. Okay, once again, mole fraction is what? The total amount of stuff in it along, yeah, remember here we have a times 3. So we have to multiply the number of moles of potassium by 3, because remember it's made of 3 parts, right? So if there are 100 of these, that means there are what? 200 of that and 100 of that, because they each made out of 200 of these and 100 of that will make it out 100 of this, right? Okay. So there's 1 makes into 3 parts. That's why we have to multiply that amount of potassium phosphate times 3. Okay, that's where the Van Hoff factor is applied. Okay, if this was sugar, not potassium sulfate, but it was sugar, then you would have put what? 1. So you can already see If this I number, Van Hoff factor number, is greater, then you will have a what? Less amount of things get evaporated. Okay, that's a general idea. Okay, looks like we are running out of time. Okie dokie. All right, like we have like 2 minutes left. Hopefully this kind of explains the basic idea of it. I don't think we have enough time to go in further into this. So let's kind of briefly look at this here. Okay, this is a change of temperature of a boiling point. Okay, so delta in chemistry means change. So delta T, change of temperature of a boiling, is equal to K, this is a constant value of whatever that solution that you want to be measuring of a boiling. M is a molality, not molarity. There's a difference between molarity versus molality. Okay, I, this is a Van Hoff factor. Once again, we talked about, right, how many sub ions are made out of it when it's dissolved. Okay. Same thing for freezing point too. Same equation except it's just TF. Okay. So basically, once again, as a general convention, if you have a lot of stuff that's dissolved in water, okay, a lot of stuff dissolved in water, you will basically what? You have a boiling point, right? Boiling point will increase, and freezing point will decrease. Okay, it takes longer time to dissolve. Okay. All right. Looks like we have less than a minute left. Hopefully this kind of clarifies everything. I'll actually upload this to YouTube so that you guys can watch this and watch it again and get it cleared. Okay? Talk to you guys later. All right.